All righty then. We've got a homework 6 that's due.
Mine was on Word.
I beg your pardon? Can you hear me okay?
Yep.
Yeah, we can hear you.
Okay. Yeah, we got a homework 6 due on Monday. And in our last class, I was using the iPad and I found I just didn't have enough space in order to be able to do uh, the kind of exposition that I wanted to. So I'm going to switch to paper and pen. And I'd like to revisit problem number 10. In this one, I think what we had was a an 8-to-1. Let me just see if I can get that to work. So we had 0, 1, 2, 3, 4, 5, 6, 7. I missed. Shoot. And now we have an output. And then there's inputs. And then the inputs to the 8-to-1 mux. And this is problem number 10. These are hooked to ground. D4 is hooked to ground. And D5 and 7 are hooked together. And they go to plus 5 volts. And then D3 and 6 are hooked together. And they are set to D. And so these go to A, B, and C. And what we have off to the left is a little counter. And it looks like it's a 4-bit counter. And it's driving A, B, C, and D. And we can see the D input is driving inputs 6 and 3. And so then the question is, how do we analyze this circuit and reverse engineer the truth table? And so what you do is you assume that you have a 4-variable truth table. And the reason you do that is because you got A, B, and C driving your selector inputs, and then you got D, the least significant bit, driving these other inputs. And as D changes, the output will change. We'll call the output Z. So what we'll do is we'll set up the 4-variable truth table, and this is why I needed paper, because you just don't have enough space if you use an iPad. It also comes out a little bit neater to use the graph paper. You can kind of see why something like this doesn't fit very well on an iPad. And what you want to do is, because the selectors are A, B, and C, and the input is D, is you isolate the selectors right in through here. So when selectors are 0, 0, 0, you isolate 2 rows at a time. Because the selectors are consistent here. So this is input 0, 1, 2, 3, 4, 5, and 6. So now when we look at the output Z, we can see the input 0, 1, 2, and 4, which correspond to here, 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 and here are all tied to ground, which means they're all 0. So these are all 0. And then when you take a look at 5 and 6, they're tied together and they're all tied to 5 volts. So they're all 1. So here's 5 and 7, 5 and 7, all 1. So then the only thing left over is 3. And according to this, 3 is equal to D. So here's D, 0, 1. And then the other thing that's left over is 6. And here's 6. And it's also wired to D. So that's also 0, 1. And that is how you reverse engineer the 8-to-1 multiplexer given the setup, and how you get the spec on the truth table. And if you like, you can even summarize this by numbering the truth table. And then say that Z is equal to the sum in canonical sum of products shorthand notation of everywhere there's a 1. 7, 10, 11, 13, 14, 15. And now when you take a look at the answer, it says 7, 10, 11, 13, 14, 15, which is exactly right. And so that's a way in which you can summarize the specification on this circuit by doing a form of reverse engineering. How does that grab you? Who got confused? Be honest.
Professor, I'm a little bit confused. Would you be able to run through it again quickly?
Yeah, sure. So the problem in homework 6, number 10, is that we're given an 8-to-1 multiplexer. Some of its inputs are wired to ground. Some of its inputs are wired to 5 volts. When we wire it to ground, it's a 0. When we wire it to 5 volts, it's a 1. But then there are these others, like 3 and 6, which are wired to D. So what we do is we create the 4-variable truth table, and we group the selector inputs over in here by 2, because for inputs 0, 0, 0, we'll be looking at the potential for the input 0 to be either 0, 1, D, or D prime. Those are the only options we can have right in through here. So what we'll do is, actually, you could probably make it even more complicated, but that's enough for now. We group by 2, and here is input 0, right? There's input 0, and we see it's going to ground. Therefore, it doesn't matter what D is. Z will be 0 because input 0 is 0. Here we go to input 1, which is here, right? So that corresponds to that. And then that's going to ground, so that must mean the output 0. Here's input 2, right through here, input 2. That goes over in here, and that's going to ground, so that must be a 0. And now here comes input 3, and that's interesting, right, because it's different. And that goes to D, so that means we have to take whatever D is over in here and copy it over to there, to the output. That's the key, right in there. Here's 6, which is doing the same thing. It's wired to D. Therefore, we have to take D and copy it over to the output. The other stuff, which is all wired to 1, because it's wired to 5 volts, we could say, well, look, 5 and 7. Here's 5 and 7 right through here. They're all wired to a 1, and therefore the output must be 1. And so for 5, which is right in through here, and 7, which is right in through here, the output's a 1. So after we're done with that, we number the truth table sequentially. And this is numbered with input selects. Well, let's say mux inputs. X inputs. So those are mux multiplexer input numbers. These are truth table row numbers. And so then what I do is I find out where the ones are in my truth table, 7, 10, 11, 13, 14, 15. And I write them down, 7, 10, 11, 13, 14, 15. And then this canonical sum of products shorthand notation is the specification for that circuit. So what we have done is we have reverse engineered the circuit to create the canonical sum of products shorthand notation. Similarly, you could take this circuit, take this spec and come up with any one of a number of different possible implementations, including the 8-to-1 multiplexer. So you can go back and forth with these things. And you could probably do it with well, a 16-to-1 multiplexer as well, if you like. It depends, you know, what you have in the drawer and what's convenient. What do you think of that? Did I answer your question? Was that Abe who asked that question? Abe, did I answer your question? I'm not sure whose question that. Who's still confused? Yeah. Let's try another example. I'm going to go and I'm going to work the example forward this time. Right? Let's start with a fresh sheet of paper. I'm going to work the example like this. And this is not in the homework, okay? But this is something you should know how to do. 1, 3, 6, 7. Okay. Given the canonical sum of products and shorthand notation for the following specification in find an implementation using an 8-to-1 mux. Okay. Who wants to give this a try? I'm gonna write an 8-to-1 mux. 0, 1, 2, 3, 4, 5, 6, and 7. So you number it first, and then you draw the box. That's easier. And you have enough space. A, B, C. Here's the output. We'll call it F. And what should the input be? Abe, why don't you tell us what you think the input should be? Are you with me, Abe? Cool. What do you think the input should be?
So 1, 3, 6, 7 would be ones.
Okay, and the others are all 0, right?
Yep.
All right then. And that's a basic implementation. Now you can go from here to there or from there to here, but suppose I said, I don't like the cost of my 8-to-1 multiplexers. Can you save me a little money and do it with a 4-to-1 multiplexer? So here's a 4-to-1. And what we'll do, and we'll write the same thing, F. Let's see, let's try someone else. Alex, what do you think we should do here? I want to implement the same thing with a 4-to-1 multiplexer. Are you with me, Alex? How about Alexa? Any ideas, Alexa? Andrew, how about Andrew?
Sorry, could you just repeat the question?
Sure. So given the canonical sum of products in shorthand notation 1, 3, 6, 7, find an implementation using a 4-to-1 multiplexer. What should I do?
I'm a little confused. Sorry. Would
That's
you
all right.
maybe this, we wouldn't have to do like the repeated division, right? To like find the smaller We could
Yep.
just use like the 1, 3, and this. Would it just be a 1 and 3, or on the 1 and the 3, or no?
Well, the way I approach the problem is we write out a truth table, A, B, C. And then we write out F. So let's write what we know. 1, 3, 6, and 7. 0, 1, 2, 3, 4, 5, 6, and 7. 1, 3, 6, 7. 1, 3, 6, and 7. All the rest are 0. So far, so good, right? So you can get a truth table from the canonical sum of product shorthand notation. Now let's take the selectors and isolate them 2 rows at a time. Okay. And now it says here, F looks like C, so I put a C in here. Here, F looks like C, so I put a C in here. Here, F looks like 0, so I put a 0 there. And here, F looks like a 1, so I put a 1 in there. And this is an implementation of a 3-variable truth table using a 4-to-1 mux. Now, who's confused?
Can you please go over the last step?
Sure. So, first thing we did was we were given the specification. We wrote the truth table. We isolated 2 rows at a time. This would represent input 0 because 0, 0 is being used in the most significant bits on the selector. This represents input 1. This represents input 2. And this represents input 3 because 1, 1 is a 3, and that's being used for AB. Now it says here F is going to be 1 no matter what C is. So I put a 1 in for 3. Here it says F is going to be 0 no matter what C is. So I put in a 0 for that. Then it says here F is actually changing and it's equal to C. So I put in a C over in here. And then it says F is changing and it's equal to C. So I put a C in over here. Now, what would happen if I said, let's put in C prime? Well, if this is equal to C prime, I'd have to go in here and modify the truth table to take C and invert it 1, 0. So as you can see, you can have an arbitrary 3-variable truth table implemented with a 4-to-1 multiplexer. Similarly, you can have an arbitrary 4-variable truth table implemented with an 8-to-1 multiplexer. So that's a direct result of chapter 4. So that's kind of right out of the book kind of stuff, and is legitimate test questions as well as homework questions. Who's still confused?
I have a question about the truth table, because in the second grouping where it's numbered 1, how come it's C prime? Wouldn't it be C?
Well, I decided to change things around just to show you how C prime would change the truth table. As initially written, this was 0, 1, in which case you wouldn't use C prime. You would just use C.
Okay, sorry, I didn't see the change. Thank you.
Yeah, that's it. Any other questions? Want to do another example? Let's do a...
Can we do number 11, please?
Sure. Number 11, let's see. Let's get a fresh piece of paper here. Now, number 11 is going to require that I do a little drawing. think that's pretty close to what's there. So what happens in here? What comes out over here, do you think? Bridget, what do you think is over here where the green dot is?
I'm not sure.
Well, that's going to be A prime because A is going through an inverter. Why don't you try the next one? What's going to come out over here, do you think?
Would it be B prime?
There you go. And what do you think would come out? I'm changing colors just to sort of make things nice. What comes out over here?
Would it be not A and not B?
Well, that's an OR. So it's A or B inverted. I'm writing it over here because I needed the space. But what comes out over here, if that's A or B inverted, we invert that, and so we must have A or B. And that must be A or B over here as well, because we inverted the inverter. And now here comes B prime. So now I have from here A or B times B prime. And over here I have A or B times A prime. Everybody following me so far? Anybody got lost? So let's do a little experiment. If I cross multiply, I have A prime A or A prime B. But A prime A, that goes to 0. So now that must be equal to A prime B. And this must be equal to A B prime or B B prime. But similarly, B B prime also goes to 0. So that must be equal to A B prime. So at the end of the day, F is equal to A prime B or A B prime. And this expression is the same thing as A exclusive OR B. And when we look at the possible answers, A prime B, A B prime is a correct answer. Does everybody understand how I got that? I didn't jump to the answer, you know. I couldn't. I mean, I couldn't look at this and know what it does. But by carefully writing down what each variable is as it gets processed by these little components, I'm able to figure out what it does and then eventually use the algebraic manipulation to arrive at a simplification, which then leads me to a result. And in fact, if you think about it, this circuit could have been implemented far more easily given the equation and then re-implementing it in the following way. A prime B goes into an AND gate. A B prime goes into an AND gate. And then the whole thing goes into, an OR gate. That's not an inverter. So just write OR. So at the end of the day, that would be F. And this is a little bit easier to understand than that because this has got more extra stuff in it that we probably don't need. Who got confused by this one? Nobody? That's good. Is there any others that you'd like me to cover?
Can we
Can we go
look
over
at
9?
number 12?
I'm sorry, number 12, somebody said?
Yes.
Okay. Let's get a fresh piece of paper here.
Can we go over number 9 after 12?
We sure can. We sure can. Just a minute. I'm going to write it down here. So we're going to do 12, and then we're going to do 9. All right. So it says here in the question, a barrel shifter is a digital circuit that can shift a data word by a specified number of bits without the use of any sequential logic, only pure combinational logic. A 4-bit barrel shifter with inputs A, B, C, and D is shown, it should say. I guess I left out an important part of the sentence. The shifter can cycle the order of bits. So we can do the following. A, B, C, D can be transmogrified through the shifter into D, A, B, C, or C, D, B, C. Wait, where's A? A, B, C, D. I should do this properly. A, B, C, D. There. Huh. Or you could say something like this. A, B, C, D. Right? These are all various possible outcomes, not this one. So I got, let's see now. Oh, and maybe A, B, C, D, no shift at all. So I can have A, B, C, D, or B, C, D, A, or C, D, A, B, or D, A, B, C. I think that would be all possible combinations. And what does it say here? I can have A, B, C, D, D, A, B, C, C, B, A, D, or B, C, D, A. And the input data is shown as being input into the barrel shifter, and then it shows some outputs. And they're using a 4-to-1 multiplexer. Oh, this is very cool. Very cool. So now we've got a shift amount, which is being used as the selector. And then we have the 4 multiplexors. So what you'd like to do is come up with a specification. Let's look at the selector input, S1, S0. Let's see now, 0, 0, 0, 1, 1, 0, 1, 1. And so let's look at the outputs in terms of the multiplexers. They are all labeled the same. Oh, no, they're not. Y0, Y1, Y2, Y3, Y4. No, Y0, Y1, Y2, Y3. Okay. So if it's 0, 0, the output should be A, B, C, D. No shift. If it's 0, 1, we shift by 1. So it's D, A, B, C. If it's a 2, we shift by 2. So it's going to be C, D, A, B. And if it's 3, we shift by 3. So it's going to be B, C, D, A. So those are the outputs that we'd like to have given the following inputs. So that's kind of cool, actually. If we examine each one of these multiplexers separately as a 4-to-1 multiplexer, then what we can do is we can take this will be Y0. This will be 0, 1, 2, and 3. And if it's 0, 0 on input, the output for Y0 should be an A. And if it's 0, 1, the output should be a D. And if it's 1, 0, the output should be a C. And if it's 1, 1, the output should be a B. Now we go to the next multiplexer. This is Y0. And now, similarly, we can write BADC. And then we go to the next multiplexer. Isn't this fun? And the answer is yes, Professor Lyon. This is so much fun. Look, if you don't think this is fun, then I feel sorry for you because it doesn't get better than this. It's pretty pathetic, right? So now you write this down, CBAD, and your barrel shifter is nearly done because now we have to do Y3. And we write DCBA. And there's your little barrel shifter with 4-to-1 multiplexers. So this is a 2 input barrel shifter that is doing a 4-bit input with a 4-bit output. Now, if I have a 3 selector input barrel shifter, can we use 8-to-1 multiplexers? Here we had to have 4 for a, well, you needed 4 multiplexers for 4 bits. If you wanted to have 8 bits, obviously you would need 8 multiplexers. And if you wanted to be able to have a 3 selector input barrel shifter, you'd need 8-to-1 multiplexers. And so you would have 2 to the 2, which equals 4 outputs. And the selector inputs can be controlled with the 4 outputs of the 4 multiplexers, if you like. So this ends up being a way to scale the problem. So if you say, oh, I got a 4-bit mux, 4-bit barrel shifter, how do I turn this into a 3 selector or 8-bit barrel shifter? And so now you've got S2, S1, S0. And now you have Y0, Y1, Y2, Y3, Y4, Y5. This is why you need 8 of these things. Y6, Y7, right? And then if you don't shift at all, it's going to be A, B, C, D, E, F, G, H. Then if you shift 1, it's going to be H, A, B, C, D, G. And then if you shift again, it's going to be G, H, A. I should try and keep this aligned. G, H, A, B, C, D, E, F. Did I screw this up somehow? A, B, C, D, E, F. Oh, the G is over here. See, I should have tried to line it up, but I didn't line it up nicely. What's going on here? Yeah. See, use graph paper to try and keep things neat. See what happens here? That should say E, F, there. Okay. I missed the column. But that's all right. So you get the idea. So you go and you proceed through just like you did over in here, only it's more writing. And by the time you're done, you're going to need 8 8-to-1 multiplexers. So answer to that is true. Who got confused by this? Sorry for the mess. I made a mess. That's normal for me, right? Made a mess. So the next question.
I'm confused.
You got a little confused? All right.
Yes.
So yeah, let's I'm thinking about how to salvage this, but I think the best way to salvage this, if you want to go and build a barrel shifter, you got to start with a spec. So selector inputs are going to be S2, S1, S0. Oops. If you number it, this is the number of bits you're going to shift. If the inputs are A, B, C, D, E, F, G, H, then when it's 0, you're not going to shift at all. So it'll be A, B, C, D, E, F, G, H. Now, if you shift it by 1, it's A, B, C, D, E, F, G, H. Shift it by 1 again, it's A, B, C, D, E, F, G. Then shift it again. So now you can see, because I did it neatly this time, how the outputs, I guess we'll give them a name. How about Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. So this is basically the inputs to your 8-bit, your 8 input 8-to-1 multiplexer. So if you said 0, 1, 2, 3, 4, 5, 6, 7, here's an 8-to-1 multiplexer. The inputs given selectors 0 and output going to be A, B, C. And then you do the same thing, copying this to the inputs for Y1, copy this to the input for Y2, copy this to the input for Y3, and so on until you're completed with 8-to-1 multiplexers. And that creates a barrel shifter. And the interesting thing about this barrel shifter is it will run in exactly 3 gate delays, because the multiplexer only has 3 gate delays worth of latency. You could say, well, how fast is 3 gate delays? And I could say, well, I don't know. It depends on the implementation of the multiplexer. But if we were going to the data book and looking at the old school 74151, we'd probably see that a gate delay inside of this thing would probably add up to be around, something less than 20 nanoseconds. Fast. fast. And that's old school stuff. That's the slow stuff. So if you wanted to, you could find faster stuff if you needed to go faster. But that's plenty fast for many applications. Who's still confused? This looks neater now, right? That looks better. So this is how a barrel shifter would work if you wanted to build a an 8-bit barrel shifter. Anyone still confused? So that's question number 12, was it? Yeah, and someone said, let's do question 9. Unless are there any more questions left for this? Okay.
Professor, did we say it was true or false?
Oh, I don't remember. True. A 3 selector input barrel shifter can be implemented with 8 8-to-1 multiplexers. So here's the 3 selector input multiplex barrel shifter, and here's one of 8 8-to-1 multiplexers. You need a multiplexer for each one of these outputs. Well, you don't need it, but you can implement it with 8 8-to-1 multiplexers. You could implement it other ways too. Probably use an FPGA on Quartus and get the whole thing done with software, I guess. That's what you guys do nowadays, right? You're using DE2 boards and Quartus. It's all very fancy. But if you wanted to, you would need 8 chips, 8 8-to-1 multiplexers, or you could have a dual 8-to-1 in a single package, maybe. But you might be hard pressed to wire everything up correctly if you're going to have 8 chips in a breadboard. That's a lot of breadboard space. Let's move on to, unless there's some more questions about 12, let's move on to question 9. Someone asked about it. All right, so we are given the 74154 4 to 16 decoder. Because it's a 16 decoder, I'm going to start numbering at 15 and work my way down to 0. 15, 14, 13, 12, 11. And then he says each one of the outputs is negated. And I know this because there's a little bubble there. And then he's got some sort of 4 selector inputs labeled A, B, C, and D. And then the whole thing, no, not the whole thing. It looks like there's a NAND gate. Big honking NAND gate. And it's hooked up to lines 15, 13, 11, 9, 15, 13, let's see now, 11, 9, 7, 5, 3, and 1. And the output is labeled with a 1 inside of some sort of a probe. And we want to say, given the following circuit, find the canonical sum of products expression in shorthand notation. So this is canonical sum of products, shorthand notation, such that F is equal to sigma M. And what goes into the this thing, this part? And that's the part that people want to know how to do. What do I do to approach this problem? Eric, I haven't heard from you in a while. What do you think?
I'm not really sure.
All right, well, can I use De Morgan's theorem on this?
I think so.
What would happen if I used De Morgan's theorem on a NAND gate? What does it turn into?
Oh, it would just be an OR.
Yeah, an OR with inverted inputs. So if this is equivalent to an OR, oops, I wrote an AND, equivalent to an OR with inverted inputs, the inverted inputs here cancel the inverted inputs there. So it's the moral equivalent of wiring these things directly up to an OR gate without inverted outputs, because the inverted inputs cancel the inverted outputs. So now what does that tell us about F?
It just wouldn't be inverted.
Yeah, it's not inverted. So how do I write the shorthand notation now?
I'm not sure what was given.
This is given, and we want that. So given this, find that. Find the canonical sum of products expression that best represents the 4 to 16 decoder in the following circuit. That's what it says. Anybody want to pitch in and tell us what you think?
Would it be 1, 3, 5, 7, 9, 11, 13, and 16?
Exactly. Well, did you say 16? Because we go up to 15 here.
Oh, yeah, sorry, I thought that was.
So that's right. I mean, essentially what you're doing is you're taking the product terms out of the decoder and you're adding them together. And so you just have to write them down. You've implemented a truth table that has the onset of 1, 3, 5, 7, 9, 11, 13, and 15. Now, who's confused by that? Be honest. Now's the time to ask questions. Any confusion with this? The only thing that was tricky was realizing you could use De Morgan's theorem here, and that the inverted inputs would give you, well, put it to you this way. This would be an equivalent to that, where the two inversions cancel. And so then what you'd have is logically the same as a summing junction uninverted, because the two inverters cancel each other. And that's just the 15 part of the output. Does it make sense to people? Are we all right? I could do it a different way. I mean, I could say, if you had A and B inverted, and then you put it through an inverter, it's clear that would be equal to AB. The inversion of the inversion gives you the two wrongs make a right kind of thing. It says that right here, two wrongs make a right. I don't know. Maybe they do make a right. So yeah, it's like a philosophy thing too. Two wrongs make a right. In Boolean algebra, I guess they do. Anybody confused by this before I move on? Okay, I'm going to leave that alone. What other questions can I answer? We got something, I think this homework is due Monday, end of day, so we got a little time, but be good to get, your questions answered now if you can.
Can we do 13 and 14?
13. Yeah, let's get a fresh sheet of paper here. So the word demultiplex means one into many, as well as selectors for distribution, distributor, many into one, one to many. So multiplexers, let's look at the mux. Here's a mux. So that's many to one, right? And so that's a mux. And demux or decoder, they're the same. Takes this as an enable input. And now we can see how the demux, this is a 4 to 1, and this is a 2 to 4. So we can call this a decoder or demultiplexer. We can call this an encoder or a multiplexer. So it's clear that a multiplexer is doing many to one. And a demultiplexer is doing one into many. But it's also something else. It's used as a selector for distribution. So it's distributing this input into one of these several outputs. So it's a selector for distribution. So the word demultiplexer means one into many. So we see that here. And it is a distributor. So the demultiplexer is sending a single input to multiple outputs depending on the select lines. That's what a demultiplexer does. What do you think of that? Is it clear? So it's one into many. Here's the many. And it's a distributor. So it has a selector for distribution. That's what a demultiplexer does. Does that answer the question okay? Who's confused?
That makes sense.
Okay. So then the next question I heard was 14. Did somebody want 14 as well? I think I heard 14. Says in a multiplexer, the output depends on its data inputs, selector inputs and data inputs, selector outputs, or the enable pin. So a multiplexer does not have an enable pin, so we know that's wrong. Multiplexer does depend on its data inputs. It doesn't depend just on the data inputs, however. So I have one that says selector inputs and data inputs, and that is the one that's more correct. So that's, I guess, B or something like this. So as the select input changes, that's this, the output of the multiplexer will vary according to the input. So in other words, if the selector input is 0, 0, I don't know what F will be until I know what the input is. If you say, well, this is 0, 0, the output will be whatever's on input to to input selector input 0, and you say, well, it's a 0 here and it's a 1 there, you can see how it depends on the inputs as well as the selector. You could write in here, it's C, and over here you could write C prime. And having done that, you could even derive a truth table. And here we can group by 2 rows at a time. Number the inputs. Input 0 is a 0. Input 1 is a 1. Input 2 is equal to C. Input 3 is equal to C prime. And that's my truth table, which I can then express as canonical sum of products shorthand notation. As soon as I number my truth table, and I can see it's equal to 2, 3, 5, and 6. So the canonical sum of products came as a result of not only knowing the selector inputs right in through here, but also knowing the data inputs. So these are data inputs. These are selector inputs. You need to know both in order to be able to get a full specification for this multiplexer, convert it to a truth table, and then extract and summarize the truth table into a canonical sum of products form, which acts as your specification. What do you think of that? Who got confused by this? Question 14. I need inputs, I need data inputs, and I need the selector inputs. I need both. Can't just have one. It's not enough. And there is no enable pin for a multiplexer. That's only a demultiplexer or decoder, if you like. Hearing no questions about question 14, I would move on to the next question. Is there another question? Homework 6.
15 and 16.
15. 15 says, in a 2 to 4 decoder or demultiplexer, how many select lines are required? And you can kind of see that here. These are the select lines, and there's 2. It's clear, right? I mean, if I had to do a 3 to 8, the 3 part shows how many select lines there are. If you wanted 16 outputs, you'd need 4 select lines. If you wanted 32 outputs, you'd need 5 select lines. So it's a, I don't know. You could say it's 2 to the n, where n is the number of select lines, I suppose. But it's the first part of the number of select lines is the first part of the name of the decoder or demultiplexer. Did that answer everybody's question about 15? And did somebody also say they wanted 16? 16? I wasn't sure. What was the other question that you wanted to do?
Yeah, 16.
16. Okay, 16. So then it says here, most multiplexers facilitate which type of conversion? Decimal to hexadecimal, AC to DC, odd parity to even parity, or single input to multiple output? And it's clear, right? This is single input. There's multiple outputs. That's what demultiplexers do. That's what decoders do. A demultiplexer sends a single input to multiple outputs depending on the select lines. A demultiplexer converts single inputs to multiple outputs. That's the exact opposite of what a multiplexer does, which takes multiple inputs with a single output depending on the select lines. And that's why I can drive a demultiplexer from a multiplexer. What happens is this becomes a synchronous serial interface when you have a counter hooked to the select lines on both sides, driven by a common clock. And so that enables you to do a high-speed encode and then decode over a synchronous serial line, SSL, synchronous serial line. So that's question 16. Any other questions about homework number 6? No questions? Well, you can bring your questions with you on Monday as well, and we'll try and address them there if you like. But otherwise, I think what I'll do is I'll go on to new material. Unless there are more questions about homework 6. So what you were to do in terms of your reading was to read pages 240 to 251 and also page 266. And I asked that you learn 1 and 2's complements. So if I take the book out, let's see if I can get the book. Here's the book. I go to page 266 if I can. Whoa, here goes the mic. Look out. Here's page 266. You can see we're learning how to multiply. So there's a combinational multiplier involved. But what I really wanted you guys to learn was the numbering systems so that you could handle negative numbers in binary. And so for that, what I would do is give you a brief introduction to the numbering systems that you will encounter when you try and use negative numbers. So let's start with a basic idea. We want numbers that are less than 0. So how do I do negative numbers in binary? How can I do that? Anybody got any ideas? Where would I mean, suppose I said to you, I want -7 base 10, and I want to write it in base 2. How do I do that? Put a question mark in. Any ideas about how we could do that? Kaylee, what do you think? I never call on you anymore.
I'm not exactly sure.
Well, how about this? Here's 7, 1, 1, 1. If it's positive, we write it like that with the leading 0. And then if it's negative, 1, 1, 1, we'll reserve the most significant bit as the sign bit. And if that's the case, then this is -7 and this is +7. And this is called, in the book, the sign and magnitude. Sign and magnitude. So question 1 says, which of the following is the incorrect sign and magnitude? And he writes +5 equals 0,101 plus 7 equals 1,000 plus, minus 4 equals 1,100. And which ones are correct? And we can see this
Aren't
is not.
plus 5 and plus or minus 4 correct?
Yep, that is correct. So then that would be option A and C. This is option B. And in option D, it says A and C are correct. And that is the answer to question 1. So now we have an idea about how sign and magnitude can be used. Simplest idea. This is not how we normally do negative numbers in the computer. That includes in most modern programming languages. But it is a system, and you can make it work. There is another way to do this, and it's called 2's complement. And this is the way things are done inside the computer. 2's complement. And in 2's complement, what we do is we take the number and we complement and increment the accumulator, CIA. And this is actually an instruction that used to be in the PDP-8 computer from the late 60s from a company called Digital Equipment Corporation, or DEC, and based in Maynard, Massachusetts. It's not around anymore. But these computers were pervasive, and they represented the first under $10,000 computer in 1967. Pretty cool, right? Gotta have one. And turns out you used 2's complement to represent the negative numbers because it allows you to use addition hardware to do subtraction. And that's cool. Let me show you how that works. So let's do 7 minus 3 equals 4. That looks really hard, right? So we start off this way. 0, 1, 1, 1. How do we do minus 3? Well, we take 0, 1, 1. That's plus 3. We complement it, and then we add 1. So if you complement it, you get 1, 0, 0. Then add 1, and you get 1, 0, 1. So take 1, 0, oops. Why didn't that work? Seven has got 4 bits, so I need 4 bits for 3. Sorry. 0, 0, 1, 1. Complement and then increment, and you get 1, 1, 0, 0 plus 1, which equals 1, 1, 0, 1. There. 1, 1, 0, 1. Now you add it together. 1 plus 1 is equal to 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, plus 1 is 1, carry the 1. 1 plus 1 is 0, carry the 1. And it falls on the floor. And now you're left with 4. And that's how they do 2's complement. In Java, we can write, or C, or C++, or C# if you like, we can write integer x is equal to 4. Let's do it the same way we did before. 7. Integer y is equal to tilde 3 plus 1. Tilde 3 is a monomial operator which forms the bitwise inversion of the numeral 3. And when you add 1 to it, it's the same as complement plus increment the accumulator, and that will be equal to -3. And when you do z equals x plus y, you will do 7 minus 3, and the output will be 4. Isn't that cool? We can write a Java program for that. So then, how would I find the ones complement? Let's see. 0, 1, 1, 0 is equal to 6 base 10. Right? How do I find -6? The answer is we complement and then increment. So we write 1, 0, 0, 1 plus 1. 1 plus 1 is equal to 0. Carry the 1. 1, 0, 1. And that is equal to -6. Now let's take -6 and add it to 7. 0, 1, 1, 1. 1, 0, 1, 0. I get 1, 0, 1, and 1. So that doesn't look correct to me at all. Let's see. -6 should be 1, 0, 0, 1 plus 1. That's 1 plus 1 is equal to 0. Carry the 1. You got the 1 in here. It is correct. He was asking for the ones complement. And this is interesting. I was looking at this and I was going, that's weird. It says 7 minus 6. 7 minus 6 didn't work. Not quite sure why. Now, here's -6. That's 1, 0, carry 1, 0, carry 1, 0, carry 1. Yep, it falls on the floor. I apparently didn't know how to add binary. Okay, so that's, 7 minus 6 is equal to 1. Thank goodness. I was sort of worried about that. So we now have a way to do subtraction. We can form the 2's complement of numbers. And there's a compelling argument that I should stop because we are out of time. So we're going to pick this up on Monday, and you have some assigned reading from chapter 5, and you should be reading about 2's complement and the various numbering systems. So next time we'll do 1's complement, and we'll also do the sign and magnitude drill work a little bit more, and we'll do some more 2's complement work. And I'll brush up on my addition so we can make sure we can add numbers correctly. So that's what I have for you for today. Have a good weekend. And thank you for your attentions.
Thank you.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.